So we stopped at the dilemma which direction to choose when we pass through the saddle. Right, so this is our saddle point equation. So both derivatives of imaginary and the real part of our complex value function vanish. All right, so basically what we would like to use is some limited information about our exponent function f of z. As usual, some kind of Taylor expansion, right? So that means that we are interested in such a direction that the u function, the real part, drops in the fastest possible way. Why? Because, as you remember, the exponential function, the modulus of the exponential function, is proportional to just the real part of u. But there is a danger here, because there is additional v function. And what it does, it adds a phase to our, it basically controls the phase of our exponential function. Indeed, because if we remove the modulus sign, then the real part controls the modulus, and the imaginary part, its value is the modulus of this point, term is 0, but it contains large lambda parameter in the exponent, which means that even a small change of v function may potentially lead to huge oscillations of the whole expression. Well, for example, if delta v is of the order of, is really small, is of the order of pi over lambda, say, then the change in this number would be e to I pi, so it changes the sign. So what may happen that we still have big contribution from the function, just from the u function, right, like that, sharp peak. But in the same region, v function may oscillate and may change sign quite fast, basically killing the contribution from the real part. So this should be avoided, which means that we should choose the direction of the path through the saddle point in such a way that the u function drops as fast as possible and v function changes as least as possible. So these, as we'll see in a second, these two conditions actually complement each other. So let's actually start probably from the first condition. So let's first derive the equation of the contour which leads to the fastest possible drop of u function. This part, this direction, is called the steepest descent direction. All right, so here we go. So how do we choose this direction? So let's actually take some point z, not necessarily nearly the saddle, but just some arbitrary point in the complex plane. And let's make some small infinitesimal step in some arbitrary direction, like here z, and this point is z plus dz. And let's trace the change of u function. So, well, it's pretty obvious. And the change in v function is defined by the partial derivatives at this point x. Okay, so and let's actually choose some direction. So defined by, I don't know, some vector n, some unit vector n. So now dx is nx times some small parameter epsilon, and dy is ny times small parameter epsilon. So now our task is to try to find such an x and an y that that the relief of this function drops in the fastest possible way. So we are interested that in the case when this change of u function is large as possible and negative. So we should tune this nx and y components of our directional vector. So let me actually show you how it can be possibly done. All right, so I made a small demo for you. Here we go. This is our relief function. And this is our reference point from which we want to move in the steepest descent direction. Imagine that we are some kind of climbers or something. So what would we do? We actually draw a vertical plane through our position point and the normal vector. And this vertical plane cuts the correct steepest descent path on the surface. So it's the normal vector that fixates the position of the plane. And what you clearly see is the projection of the normal on the horizontal plane, which defines the necessary direction in the plane. So now let's recall how the normal direction is defined. Well, the normal direction is the direction of the gradient, all right? So our relief of u function is defined, okay, so its altitude is defined by this function. So, or rather, we would better define it like that. So we introduce some f function, the function of altitude, x and y. It's equal to h minus u of x and y is equal to 0. So this is the definition of our surface. And the normal direction in the direction of the gradient. So it's simply df over dx, df over dy, and df over dh. Okay, so the last term is trivial, dh, sorry. The last term is trivial, it's simply 1. And these two are minus du over dx, and this is simply minus du over dy. And we are interested in the horizontal projection of the gradient function. So this is this projection. So now we know what our components of n vector are. So nx is simply minus du over dx, while ny is minus du over dy. So this is the steepest descent direction for the u function. All right, good. Now let's actually figure out what this direction means for the v function, because as you remember, we are interested in such a direction that the imaginary part of the v function, right, it changes in the least possible way. Well, actually, we prefer that it stays unchanged. Okay, let's figure out what is happening. So v of x plus dx, y plus dy is equal to, okay, the same formula, v of x and y plus dv over dx times dx, but dx is nx epsilon plus dv over dy and y epsilon. And then let's fix epsilon. We substitute nx. We plug in minus du over dx for nx and minus du over dy for ny. Okay. Let's see what is happening. So this is the initial value of our v function. And now, all right, minus dv over dx times du over dx the bracket plus dv over dy times du over dy epsilon. Well, this thing is actually has a very simple structure. So to see this, let's recall that our f function, or initial f function, is an analytical function of complex variable, and that means that it satisfies Cauchy-Riemann conditions. So here they are. Du over dx should be equal to dv over dy, and du over dy is equal to minus dv over dx. Right, and let's actually change, for example, this dv over dx can be substituted with minus du over dy. Why not? Right, so let's actually write it down. So v of x and y minus epsilon, and here we go. So dv over dx is minus du over dy, and here we go minus, and just, sorry, without minus, du over dx. And here we substitute dv over dy with du over dx, without minus sign though, right? So du over dx times du over dy. And you see what happened? What just happened? They cancel each other. So there is no change in v function at all if we move along the steepest descent direction of u function. So it's beautiful, isn't it? Because now we see that these two conditions complement each other. And so it saves our day, because now we know that if we want to estimate our integral, we just choose the steepest descent direction for u function, and there is no oscillation of phase for our v function. Good. So to illustrate this idea, let's consider some really simple example. For example, the quadratic function f of z is equal to z squared. Okay, so which is x plus iy squared. So the u function is x squared minus y squared. Now let's actually try to figure out what the curves of steep descent directions are. Okay, as we remember, they defined, the directions is defined by the following steepest descent direction equations. Okay, so minus du over dx is minus 2x, and here we have 2y. All right, and so here we have some curve in a complex plane, and this vector gives us a direction. And basically mean that if we parameterize this curve by some parameter s, or t, whatever, like s, x of t and y of t, then the tangent vector is defined by the derivative of x and y with respect to this parameter. Here we go. So this derivative is negative 2x, and this one is 2y. Okay, let me actually use this short notation like that. And what is clearly seen here, look closer. So let's multiply this equation by y, and this equation by x, and let's sum them up. So x dot y plus x y dot, and you see when we sum them up, the right hand side vanishes, and this is nothing but the derivative of the product of x and y. So these are their curves of the steepest descent, and as you see, they lead to the constancy of this product. But this product is nothing but the imaginary part of this f of z function, right? Here it is. F of v is equal to 2xy. So here it is. The steepest descent directions for u functions are the level lines for v function. All right. Okay, let me actually illustrate it with some example. So this is our typical relief of our u function. And the red lines are the lines of the steepest descent. And you clearly see that if you view them from above, they form hyperbolas. And it was the hyperbolas that we've just got from our example. So here they are. Now let's figure out what is happening near the saddle. So as we remember, the saddle is defined by the condition that the first derivative of a function vanishes. It's a critical point. df over dz is 0. So when we Taylor expand it, there is no first order term in Taylor expansion. So, and it starts with the second order expansion. And here is the picture. Oh, yeah, for example, here. And now, so this is z0 point. And we should choose z in such a way that it goes along the steepest descent path. Okay, let's make a parameterization. Z is equal to z0 plus some kind of s times e to I alpha, where alpha is precisely the steepest descent direction. It's this angle. Like that. So how should we choose it? Well, the easiest way to get it is actually to plug in this parameterization into our expansion of f of z function. All right. So what do? We substitute f prime prime with its exponential form, and we plug in this parameterization instead of z minus z0. So it's s squared times e to 2I alpha. Right. So now we are interested in such alpha that the whole thing is real because we are interested in the level lines of v. So the imaginary part of v function shouldn't change. So this change should be totally real and negative. But the real part, the real part is defined by the cosine of this phase term. So now we could write down this additional term is 1/2 f prime prime naught modulus times cosine of phi plus 2 alpha and plus I sine of phi plus 2 alpha. Right? And here we go. We require that the cosine, the real part, is equal to -1. So phi, it corresponds to the steepest descent direction, right? It's the most pronounced drop of the real part of our function. So phi plus 2 alpha should be equal to, so cosine is equal to -1. The thing is equal to pi plus 2 pi n. And as you see, if phi plus 2 alpha is equal to pi plus 2 pi n, then the sign vanishes. So indeed, there is no change in our v function. Okay. So that's it. Now we should plug it into our original expansion.